Good afternoon. I'm Professor Sever. Today we're going to do an introduction to abstract vector spaces and subspaces. What we would first like to do is prove a result that most students find to be not surprising. Lemma 1 is that 0 times any vector, 0 scalar times any vector is the 0 vector. And here's a proof for that. A proof. There are other ways to prove it. And when I prove it, notice I'm going through and I'm showing which axioms I'm using to achieve the result. So let's first note that by the additive identity axiom, 0 plus anything is itself. So this vector has to be itself plus the 0 vector. That was axiom 4. And technically I'm writing it on the other side, so really there should be the way I've written it, we should have a commutativity step here. Now, any vector, so what is 0? 0 is any vector plus its additive inverse. This is just notation for the additive inverse of this vector, and that's axiom 5. Okay. Now by associativity, instead of adding the second two vectors first, I can use associativity and add the first two vectors. Notice I'm not switching the order of anything. I'm not using commutativity. I'm just reassociating the parentheses. We can use the distributive law, which is axiom 8, to say, when you think of it this way, it's distributive. But when you look at it as being applied here, factoring. So notice, if you go from number 8, from the left-hand side to the right, what would we say? Well, that the scalar addition distributes over the scalar multiplication here, right? Well, you could also look at it from the right-hand side to the left, and you could say you can factor out in this vector sum, you have a common factor of u, you could factor out the u. So reading it from right to left, it's factoring. Reading it from left to right, it's more of a distributing, but it's the same axiom, the same property. Just depending on if you're given this and producing this, you would say it's distribution. If you're given this and producing this, then you say it's factoring, and that's what we're doing here. So we have the sum of the two vectors. Now we're going to write it as a scalar product. That's called factoring. Notice the vector u, common vector u, is being factored out here. Now, that was axiom 8. So now what's 0 plus 0? Well, there is a step here. It's not a vector space axiom, but we know in the reals 0 plus 0 is 0. And now once again, you have a vector plus its additive inverse. By definition, that's 0. So 0 times u, any vector u, is in fact the 0 vector of the space in any vector space. So any set, any algebraic structure that satisfies these 10 properties must have the additional property that 0 times any vector is the 0 vector. We just proved that. Let's look at kind of the opposite. So what if I took any number like 2 and multiplied it by the 0 vector? That should give us, again, the 0 vector. So let's look at that. Simple. There are, again, many ways to do it. I'm just using one possible method to illustrate the lemma. So what is c times 0? Well, the 0 vector we just proved is 0 times u. It's nice to use the theorems or lemmas that you previously proved. I just proved this on the prior slide. So let's use it. Let's use the tools that we developed. I've shown that 0 times any vector is the 0 vector. So I can replace the 0 vector for what I know it is. Now I can use axiom 9, the pseudo-associative axiom. I can associate the scalars. So now we have what's c times 0. Now again, this isn't circle times because this is the times of the real numbers. This is the times in the field of real numbers. This is the scalar multiple in our abstract and arbitrary land of v. So c times 0 we know is 0. So again, what's 0 times any vector u? That's lemma 1 again. That's 0. So we've proven that any scalar times the 0 vector is, of course, the 0 vector. By the way, we could do this with simple addition. I could have constructed a different proof as well, which I think I have posted in the notes. This concludes the second portion of our Introduction to Vector Spaces and Subspaces video. Thank you for watching. I'm Professor Sever. In part 3 of this video series, we will look at the definition of abstract linear combination, the definition of the vector subspace. We will provide concrete examples of well-known vector spaces, and we will go through an initial proof of showing that a subset is in fact a vector subspace.